to talk about the importance of knowing about space weather. Important to note is that our knowledge and our ability to forecast space weather is roughly in the same position where normal terrestrial weather forecasting was about 100 years ago, i.e. not very good, but we are making progress. What is space weather? Space weather describes the condition of the space environment between the Sun and the Earth, as well as the effect it has on our technological systems. This is very important because in the last 50 years, as we all know, our reliance on electronics and technology have improved dramatically, and therefore this is an important. Space weather is a consequence of the behavior of the Sun, which we can't forecast at this time, the nature of the Earth's magnetic field and atmosphere, and of course our location in the solar system. We can't change these things, but we can monitor them, and we attempt to forecast what is going to happen. It's also interesting to note that the distance between the Sun and the Earth is roughly 150 million kilometers, which is of course an enormous distance. The Sun really has two phases, an active and a quiet phase. The images on the left show the active Sun in visible light at the top and UV light at the bottom, and on the right they show the quiet Sun, the same images. And these phases come and go, and the phase is really called the solar cycle. The solar cycle is a periodic change of solar activity. This period is roughly 11 years, and we have records going back hundreds of years to verify this. And on top of that, the magnetic polarity of the Sun, i.e. where the north and south poles are, flips every 22 years. The plot you see at the bottom shows you the solar cycle. You can measure this either by total irradiance or sunspot observations or the solar flare index or something we call the F10.7 radio flux. 10.7 centimeters refers to the wavelength of radio waves coming off the Sun. The variation is very small because if you look at the scale on the left-hand side, you see it's all roughly around 1366 watts per square meter. So the actual variation of the output of the Sun is only 0.1% over an 11-year cycle on average, but the impacts of that are absolutely enormous. Sunspots, which are easily seen, these are darker regions on the solar surface because they are cooler. And over a solar cycle, the sunspots move towards the equator. I don't know why that is, but it's a long observed phenomenon, and you get the so-called butterfly diagram that you see at the top of the panel, where in the early part of a solar maximum phase, the sunspots appear at higher latitudes, and then over time of a few years, 5 years, they proceed towards the equator, and then the whole thing repeats itself again and again. The panel at the bottom in black just shows the average daily sunspot area, which of course goes up and down with an 11-year cycle, depending on the number of sunspots and their size. And this shows again very clearly the solar cycle for the last 3 cycles. We have records going back at least 24 cycles times 11, so it's roughly 250 to 300 years. You can see there's a lot of variability, but the 11-year cycle is very obvious. You can also see that from cycle 22, 23 to 24, the maximum has been decreasing. These long-term maxima and minima have been known from the past. Right now, the Sun seems to be going into a rather quieter phase than it was at the turn of the century, the turn of the previous century. And there are 3 basic phenomena that we have to keep our eye on with regards to the Sun. One is solar flares. Solar flares are a sudden flash of brightness, which usually lasts a few minutes. And this consists of a large amount of X-rays and UV light coming off the Sun. And because it's photons, the transit time between the Sun and the Earth is 8 minutes at the speed of light. The amount of energy released is absolutely enormous, 6 times 10 to the 26 joules typically. which for comparison purposes is the equivalent to 50 billion, yes, 50,000 million Hiroshima-sized nuclear bombs going off at the same time. During solar minimum, the frequency of these events is roughly less than once per week. During solar maximum, they can be several a day. The picture on the bottom right shows a typical solar flare and the Earth imprinted upon the image to the correct scale. So the flares are very large. And we know they produce X-ray and UV flux because they've been measured by satellite. That's shown by those red and blue graphics from the GO satellite and geostationary orbit. Then you have coronal mass ejections. So these are not photons, these are actual particles now. Large ejection of charged particles up to 10 to the 10 tons. So that's 10 billion tons. The average mass is around 1.6 billion tons. And these go off over a duration of several hours. Particles then move across space towards the Earth at velocities that vary from something like 20 to 3,200 kilometers per second, averaging around 500 kilometers per second. So it takes between half a day and 5 days for those particles to reach us. During solar minimum, they occur at roughly once per every 5 days, and during solar maximum, they occur roughly 3.5 times per day. And again, the pictures show a coronal mass ejection coming off the sun. They typically have those looped type shapes to them because of the magnetic field, and to scale, there's the Earth shown on the image. Important to note is, although there are lots of solar flares and lots of coronal mass ejections, not all of them propagate towards the Earth. The sun being a sphere, it means that these events can go in any direction, and sometimes they have no impact on us whatsoever. So I'm going to show a video clip. I'll let it run. It's on the right-hand side. These are images taken from the SOHO satellite using the LASCO coronagraph. The coronagraph allows us to take images of the solar wind. There is a disk which blocks off the sun, otherwise it would overload the instrument. The white circle shows you what the size of the sun would be in the image. And what you see is a lot of particles coming off the sun, and those bursts that you see coming off periodically are coronal mass ejections. Of course, the video is running much faster than real time, as shown by the timestamp in the bottom left. The picture on the left in blue, although the color is not important right here, just gives you an idea of the scale. That image encompasses only 10% of the distance to the Earth, about 15 million kilometers. So we're talking about very, very large scale events here. We can measure these particles coming off the sun. It's mainly electrons and protons. The protons interest us more because they have a higher mass and can cause more damage. And they have been measured also using the GO satellite, which has a detector on it for measuring the flux. And you can see in the red, blue, and green curves very clearly the sudden increase in that flux. GOES is a geostationary orbit, so it's really close into the Earth. It doesn't serve for forecasting, it just tells us what is coming. If one of these events comes towards the actual instrument, so those are the blue images on the right, so you can actually see at image number 4, there's a large snowing effect. And that snowing effect is the actual particles, the protons, hitting the CCD detector of the actual coronagraph. So these are actual direct impact events on the detector itself, and I'll come back to that later. The video clip shows us very clearly. Clearly, if you're looking towards the sun, you normally see coronal mass ejections going off in directions that are not towards the Earth. But if the coronal mass ejection comes towards the Earth, the records that we have of solar proton events or solar energetic protons go back to around 1600. We use proxy records, tree rings, ice cores, that type of thing. And they show that these high energy events are not that uncommon. They're not frequent, but they're also not that uncommon. The event, Carrington Storm of 1859, which was observed by Carrington here in the UK, was so large that he actually observed it with the human eye. Subsequent events have been observed by instruments. None of them have been as big as the Carrington event, but they are also still significant. More recent events were the Bastille's Day Storm in 2000 and the Halloween Storm in 2003. And then we have coronal holes. Coronal holes are regions where the solar magnetic field does not close. They allow protons and electrons to escape the sun because they're not trapped by the magnetic field, and they constitute what we call the solar wind. And I'll moment. This means the sun is losing weight at around 1 million tons per second, which is absolutely enormous. And that's the background. That's what's happening all the time. And then you get the coronal mass ejections on top of that. But given the enormous mass of the sun, 10 to the 30 kilograms, just on mass loss alone, the lifetime of the sun would be 30,000 billion years. So we don't have to worry about the sun losing weight and disappearing on us at this time. You have the solar wind, which is of course made up of protons and electrons mainly escaping the sun. The density in space is very low, only 1 to 10 particles per cubic centimeter. And it's got two components: the slow wind at 400 kilometers per second with a temperature around 1.5 million Kelvin, and the fast wind at around 750 kilometers per second. And we've measured this using the ACE satellite, which has now been replaced by the Discover satellite, and that is parked about 1% of the distance between the Earth and the Sun. So it's in space looking at the Sun, and measurements have been going on now for many years. And we find that the solar wind is mostly benign, but occasionally it is stormy. In that sense, it's rather similar to the weather we have here on Earth, except that it's made up mainly of charged protons and electrons traveling at very high speeds and at high temperatures. So the first thing that we would be interested in terms of our technology are the radiation belts. These were discovered by Van Allen in 1958 during one of the very first satellite missions from the USA. These are two donuts of radiation which surround the Earth in space. There's the inner belt, which is mainly made of high energy protons, and the outer belt mainly made of high energy electrons. And the radius of these belts around the Earth is given in a unit called RE, which stands for Earth radius, and the radius of the Earth is 6,730 kilometers. So the inner belt is quite close in, less than 2 Earth radii. The outer belt is further out, 3 to 7 Earth radii. In the geostationary orbit, where most TV satellites and so on sit, or Earth observing satellites might be, is at 6.6 Earth radii. So almost all satellites we're interested in fly in and around the radiation belts. That's why we're interested in them. The plot at the bottom, the color panel, shows very beautifully the flux of high energy electrons in the radiation belt. That's mainly for the outer radiation belt, and you see it's highly variable. And that's very important. It goes up and down according to storms. And radiation is extremely dangerous for humans as well as satellite electronics, and it's unavoidable. Other thing that comes from radiation from the solar wind is, of course, the auroras. That's another long and completely different story, which I won't go into now, but it's very, very beautiful, and mainly you can see them at high latitudes, although we can also see them from the UK and certainly from the northern UK or Scotland. The picture on the right is a satellite image from the NASA image satellite to show you the large scale of the auroras over Antarctica. I will leave it at that. So now to do with the impacts. Coronal mass ejection. The impacts that we might experience are effects on HF radio communications, satellite navigation, timing for industry, magnetic navigation, industry, especially aviation and oil drilling, which rely on magnetic measurements, electric power grids and pipelines, satellite drag, which goes to satellite lifetime, and of course the auroras, which are beautiful to look at. And I'll go through some of these in a moment. For solar energetic protons, there's an increase in ionization of the high latitude ionosphere, and this disrupts radio communication, which impacts on airline, civilian, and defense radio communications, aircraft radiation exposure that we all get when we fly, astronaut survival, and satellite failures due to electronic failures. And then solar flares also increase the ionization in the ionosphere, which also disrupts radio communications, mainly on airlines, civilian and defense, and satellite communications. Just so that I mention it, the ionosphere is the charged part of the atmosphere, which typically ranges from about 50 kilometers up to 1,000 kilometers. It only constitutes about 1% of the ionosphere, but it has a very big effect on radio communications and navigation. And of course, all signals from spacecraft have to pass through it to reach the ground. On HF communications, I've mentioned this just a moment ago. The plot on the left shows the altitude versus the electron density. You have two basic profiles, the green for solar minimum, the red for solar maximum, and of course day and night, but it's highly variable. It's not always the same from day to day. These electron density profiles with altitude determine how far you can send a signal, especially if you're trying to transmit over the horizon, and also the losses of the signal, both of which are terribly important for ships and aircraft alike. We can produce these maps. These maps show where the signals are likely to be weak or strong, what the losses are. This plot with the map of the world on it shows the highest frequency affected by 1 dB of absorption. A dB is measured in this case as 10 log 10, so 3 dBs would be half the signal strength, so on. 10 dBs would be a tenth, 20. What's important are maybe those two bar graphs on the right. One is during a solar flare and one is during quiet times. If you wanted to have radio transmissions with a loss of less than 10 dBs during quiet time, you would be able to go up to just over 15 megahertz, just about 15 megahertz. If you wanted the same during a solar flare, you'd only be able to go down to approximately 30 megahertz. So the solar flare has restricted our ability to have radio communications either through the losses or through the choice of frequency in this one example. This is very important for aircraft communications. The amount of aircraft communications, aircraft have to be in communication with the ground at all times. No interruptions are permitted at any time for safety reasons. In the past, for that reason, aircraft did not fly over the polar regions because there just weren't enough ground stations and airports available. Now, with the reliability of aircraft improving, we can do this, and of course, it's much more efficient in terms of fuel and time. And the number of transpolar flights has increased dramatically. Now, the problem with flying over the pole is that you cannot rely on satellite communications or ground VHF communications. Above 80 degrees, you can't see satellites. 78 degrees, there are no VHF communications. So you have to rely on HF communications, frequency communications, so that you can do over-the-horizon communications with your aircraft and your controllers. But these HF communications are badly affected by forecasting. Is very important to allow flights to fly over polar regions. Likewise, aircraft radiation dose. If you fly during a major storm, you're going to get a dose of radiation. Certainly, aircraft fly higher now than they ever have done before. As a result, radiation goes up. For a flight crew, your typical dose over a year will be around 2.2 millisievert. This is an accumulation of flight doses of individual flights, which are roughly 2 to 10 microsievert per hour. To give you a feel for what that is, a CT scan is around 1 to 10 millisieverts, and X-ray is up to 0.1 millisieverts. The dose limit allowed in the UK is around 20 millisieverts for the nuclear industry worker and about 1 millisievert for an ordinary civilian. And again, for comparison, the radiation dose for survivors of the Hiroshima atomic bomb was around 5 to 20 millisieverts. So the average passenger is unlikely to accumulate a dose that could be considered dangerous, but crew definitely can fall into that category, and they do monitor radiation on flights, and crew then get laid off or furloughed until their year is up if they reach the maximum dose allowed, and then they can fly again the following year. It's very important for safety. I mentioned earlier that electronics can be affected by protons impacting on the detectors. We saw that snowing effect shown bottom left. This is true for any electronics. The snowing effect you see visually there is, of course, a sign of charging. That's because the protons are impacting on the substrate of the electronics. This not only can change the state of the electronic, so you can switch things on and off or change the memory, but it can also degrade the electronics permanently. And you see bottom left how a typical solar panel array degrades over time so that it loses a significant amount of performance after several years. 5 to 10 years is more or less the end of useful life. In terms of memory upsets, the plot on the left shows an example over several years of where memory upsets occurred for one satellite, the Sumbandila sat, and it was found that roughly half of all memory upsets, unwanted changes in memory, occurred in one specific region that's shown by the purple dots, and that corresponds almost exactly to the region that we call the South Atlantic anomaly. If you look at the top right, you see a graphic of the Earth's magnetic field strength, and over Eastern Brazil, you see that the magnetic field of the Earth is at its minimum. So Brazil, Southern Atlantic Ocean, and the tip of Southern Africa, Cape Town area, is a region of low magnetic field with high radiation. And we know this because if you look at the radiation map at the bottom right, you see very clearly the two long horizontal curves which represent where the radiation belts map down to the atmosphere. But then you see also a radiation blob in the South Atlantic, which corresponds to the magnetic anomaly. We move on to astronaut survival. This plot shows very nicely the Apollo missions from Apollo 7 to Apollo 17. Of great concern was, of course, that the astronauts should survive, and they all did. However, you see also solar proton events that have occurred in the form of blue bars, and the intensity of those events could either raise your cancer risk, bring severe radiation sickness, or in one case, halfway between Apollo 16 and 17, instant fatal dose would have occurred and death would have occurred in flight. So had one of those missions gone during one of those storms, the astronauts would have had no way back and they would have been in deep trouble. The other lines, the red line shows the maximum annual dose allowed for radiation workers, and the green line shows the average annual dose allowed for civilians at the Earth's surface. We can go back many years to have a look at solar energetic proton events since Apollo, and you can see that there are many events that occur that are above the green or the purple line, and they are in the sort of category of raised cancer risk, and some of them in severe radiation risk. So this is a real problem for spaceflight, and going to a place like Mars, which is 9 months flight away, and in 9 months you're definitely going to find yourself stuck in a storm. It's unavoidable. Solar storms also affect satellite lifetime. What happens is the storm arrives, as shown in the plot on the left. That big spike in the black curve shows when the storm arrived. It heats the upper atmosphere. The atmosphere then expands. That creates additional drag, which then slows the satellite down, causing it to fall out of the sky. This is particularly the case for low Earth orbiting satellites below 800 to 1,000 kilometers, and it can dramatically shorten the useful working life of the satellite. If you look at the plot on the right, I've drawn one example in red. It's the International Space Station, which is at 400 kilometers altitude. During solar minimum, the lifetime would be roughly 3 years before it fell without boosting. During solar maximum, the lifetime would be around 0.2 of a year. So we're talking about 3 months lifetime before it would fall out of the sky without regular boosting. And during storms, the same thing can happen. So low Earth orbiting satellites either can have their lifetime shortened or they need boosting to keep themselves up in space. GICs, this is geomagnetically induced currents. You have a very large flux of protons and electrons bombarding the top of the atmosphere. Moving charges constitute a current. The current typically flows around 100 kilometers altitude. That current can then generate a magnetic field. That magnetic field induces itself into power lines. This is a common problem, especially at higher latitudes like Scandinavia, northern UK, Canada, and so on. And what you're doing is you're pushing into the system an unwanted current. And that unwanted current can then overload the transformers in the system by overheating them. So this is a typical example. The pictures at the bottom are from Eskom. That's the South African energy generator from the storm on 29th of October 2003. And you can actually see pictures of burnt out transformers as a result of overloading. And the costs are enormous. Each transformer is worth around $10 to $13 million. And it takes 12 to 18 months to replace one because they're all made to order. You just don't buy them over the shelf. The big storm of March 89, the Quebec power grid collapsed within 90 seconds and cost Canada $2 billion to put back into operation. The Halloween storm of 2003, South Africa lost 15 400 kV transformers to that one storm alone, at a cost of around $10 million apiece. And this happens repeatedly in other scenarios. These are the two that happen to be in the open literature. Solar storms affect satellite navigation. We rely on the American GPS system, but there's plenty others out there as well from Russia, China, India, Galileo, which is the European one. These systems consist of 24 satellites with some spares. The cost of building them is huge, $12 billion. The cost of operating them is about $2 million a day, but we're highly reliant on them now. So in the GPS system, the SatNav system that we're familiar with, the accuracy during quiet times is around 10 meters horizontal, storm times 30 meters. And more importantly, the accuracy in the vertical direction goes from 17 meters in quiet times to about 50 meters in storm times. And this degradation accuracy is very important because we are relying more and more on satellite navigation for aircraft, especially aircraft landing, as well as flying drones, which are now becoming a great economic hit. And if you degrade your navigation from 17 to 50 meters whilst you're trying to land, you can just imagine what might happen. On top of that, the figures are absolutely enormous of our reliance now on SatNav. You can see even in 2017, The economy around the GPS system alone was over $750 billion and still growing rapidly. Solar storms, due to gusting of the solar wind, can cause what we call scintillations in the upper atmosphere, in the ionosphere. This is very equivalent to the twinkling star effect. What it does is it causes ionospheric electron density variations, which causes the refractive index to vary, which perturbs the path between the satellite and the ground. For navigation purposes, this can dramatically and rapidly, over a period of only a few seconds, change the signal that you're getting. And we now know that 3 to 4 airplane crashes every year are due to a controlled flight into the ground. What does that mean? It means there was nothing wrong with the aircraft. It just didn't know where it was. And it didn't know where it was, in some cases, due to scintillations in the ionosphere, causing the navigation system to break down. The pilot didn't realize this was happening, and the aircraft hit the ground. So this is a serious problem that we face in terms of navigation. So now, in the final phase, vulnerability, I only have data from 97 to 2012. I'm sure it will continue to more recent years. Our populations increased by 20%. Our electricity consumption has increased by 6%. The global satellite industry revenue has increased by 320%. There are over 1,000 satellites operated by 50 countries now. In the US owns a quarter of them, and they're worth around $250 billion alone. And we estimate that the space weather annual cost in the USA alone is about $5 to $10 billion due to communications and navigation failures. Extreme geomagnetic storms, which occur roughly once every 100 to 200 years, are of particular interest. We believe it will affect about 10% of the world population for up to 2 years. Roughly 10% of all satellites will remain inoperable for hours to days, some of them permanently. The USA have estimated the cost of an extreme event will be around $1 to $2 trillion per annum. We're talking now numbers that are of the order of the size of the UK national budget. Power blackouts, when they occur, cost $4 to $10 billion a day in terms of lost productivity. If airlines have to divert aircraft because of communication losses, that's roughly $10,000 to $100,000 per aircraft. Bearing in mind, pre-pandemic, of course, there were 100,000 flights a day over the Earth. And then, of course, there's the radiation dose in airlines of around 20 millisieverts. Severe space weather vulnerability is so high that the UK has generated a national risk register. This is from 2015. I have circled it there in red. The severe space weather effects are the second highest risk that the UK government believes it faces, other than the pandemic influenza. Of course, we don't have a pandemic influenza right now, but we do have a pandemic. The only thing that is below that in terms of risk is severe space weather, because of the hidden impacts to our technology, navigation, communications, and so on and so forth. So it's very important for us to try and forecast when space weather storms are coming and what the impacts are going to be. So what's the event probability? Of course, space weather is mostly mild, but occasionally stormy. Storms only occur for roughly 5% of all days in a solar cycle. When a storm occurs, around 59% of all satellites experience a failure. They see very clearly a 20 to 60% increase in insurance claims, mainly associated with electrical failures. There's a 10 to 40% increase in unexplained power grid disturbances. And roughly 4% of all power grid disturbances are attributed directly to GRCs after the event. It's interesting to note that our vulnerability, taken as an average over 60 years, 65 years, is greatest in March and September, and is least in the winter and in the summer. That's to do with the magnetic geometry of the Earth as it orbits around the sun. European Space Weather Agency has done a study on mitigation, and they've done a cost-benefit analysis for the European Union. If we're able to forecast space weather events, we can save money. It's around €1 billion, mainly for the power line and airline industry, €100 million for the space industry. That's because they're much more aware of space weather effects, and then the other items have much lower value. So there is real value in studying space weather storms and their impacts on us. And then by way of conclusion, this is the second to last slide. Space weather superstorms are rare. They occur in roughly 1 in 100 to 1 in 200 years. However, I note that the last superstorm, the Carrington superstorm, occurred 156 years ago. So we're slam bang in the time frame when we expect the next one to come. And the impacts of superstorms can be severe. Space weather, major storms in space weather are common. We get a few of them annually, whether it's solar minimum or solar maximum, and the impacts of a large storm can be very expensive. And then finally, I wasn't able in the presentation of this talk to really bring anything of my personal work in. So I've got this one slide here which says space weather research is fun. And I've been doing space weather research now since the early 1990s, 1991, and it's enabled me to do interesting things and go interesting places. This is an image taken of myself when I visited the South Pole a couple of years ago as part of this project effort. And yeah, I'm going to end there. Thank you very much.
Mike, thank you very much for that amazing summary of how space weather can affect us. It is quite significant. But right, I'm going to ask Dave Cotton now to summarise the questions.